Now that we have a basic understanding of the process, it's time for us to start planning and preparing to make a mold. You might think the first step of this process is to start building a mold box or even mix up our material. But before we get to that, we need to understand how to think about mold making. If we don't stop and get our head on straight, we'll find ourselves making critical oversights in our design. Those oversights often lead to beautiful molds that don't work at all. Mold making is different from many production or making processes because we have to think upside down. When our mold is finished and ready for casting, it's usually positioned upside down for pouring. That means the master object, the object we're making a mold of, is also upside down inside the mold. If we don't plan around this, our casting material might not fill up our mold properly, or our castings might be impossible to remove from our molds. That's a lot of wasted time, material, and effort. An easy way to get yourself started off on the right foot is to turn your master object upside down. Doing so will allow your brain to see some potential problems like undercuts or narrow sections or small fragile components. If your master's too heavy or large or just generally unstable upside down, then an easy trick is to take photos of your master object and simply rotate the photos afterwards. This also gives you great reference for images that will come in handy later on in the process. In order to get our casting material into our mold, we'll need to make sure that we have an effective plan for pouring. Many masters have a flat base, which means our final molds will have a convenient opening to pour our material into. Other more complex molds, like two-part molds, won't have this luxury, so we'll need to account for this in our design. Now that we're thinking upside down and accounting for pouring, the next mental shift is to start accounting for air release. When we cast in our molds, we're usually pouring a liquid or semi-liquid material into them. That means we're swapping the air that's inside of the mold for that new material. To make sure we have clean and beautiful castings, we want that exchange to be 100% complete. If we have any air trapped within our mold, the cured casting will have that particular section completely missing. And that means a not so good final product. To ensure an air-free design, we'll do something called master scanning in order to pinpoint problem areas and plan around them. We'll go into more detail on that process in another video. The last consideration we need to make is to think about removing our master and subsequent castings from our mold. If we don't think about removal, then we risk having our master stuck inside with no hope of removing it without damaging either our mold or the master itself. If our master comes out easily, then it's a good sign that our castings will come out of our mold just as well. Let's review the mental shifts that we need to make. 1, thinking upside down. 2, planning for pouring. 3, accounting for air release. And 4, designing for removal. In mold making, we often categorize the types of molds by the number of sections or parts that it has. If the mold is just one solid piece of silicone rubber, we call that a one-part mold. If it's 2 pieces, then we call that a 2-piece mold. 3 is a 3-part mold, so on and so forth. For most of our beginning mold making projects, we'll be using 1-part and 2-part molds, so let's talk about each one so that we understand the differences and benefits of each. A 1-part mold is the simplest mold design there is. Since it's just one piece of silicone rubber, we only have to pour one time. A single pour means our mold is done much faster than the other options. Since the entire mold is in one piece, we don't have to worry about the complexities of fitting 2 pieces together or accounting for odd pouring locations or seam lines. All topics we'll cover in detail in our 2-part mold making course. 1-part molds are great for objects that have a flat base that we can utilize to remove the object easily and to pour into. 1-part molds can also be cut in specific ways, resulting in what's referred to as a cut mold. However, there are downsides to 1-part molds. Since we have to remove our object and pour into a flat section, we cannot capture every detail on every surface of our master. Additionally, when we demold castings from a 1-part mold, we often have to stretch and flex our silicone to accomplish this. That puts more stress on our molds and can lead to tearing and other issues if not planned for. For objects that have detail we want to capture on every side, we have to look at multi-part molds, most commonly the two-part mold. Two-part molds encapsulate the master completely in silicone. That means we capture every detail on every side of our master. This process is done in two sections, and both sections must be allowed to cure individually. The end result allows us to simply separate our mold halves to remove our castings easily without stretching or tearing our silicone. However, we do have to account for new challenges that arise with two-part molds, including pore spouts, seam lines, registration marks, proper casting positioning, and a few others. All of this is more than manageable with a little planning ahead of time. Other unique types of molds include brush-on molds and matrix molds, just to name a few. These require a different set of skills and knowledge, but are great for very large or very complex projects. In this course, we'll be focused on the basics of silicone mold making, so that we'll be set up for success when we start to attempt more complex molds like these. We've been using the term master for a little bit now, but I want to give you a clean definition of what it means. A master is the original object that we're going to make a mold of in order to make duplicates or copies. You may hear a few other names instead of master, including buck or hero. Don't get too hung up on the names. If you know the definition, then you'll be able to handle whatever name someone throws at you. When starting our mold design, we want to look at our master and review a few key attributes. Number one, what is the overall size of our master? Number two, what material is our master made of? And number three, what are the basic areas of our master? Our first step is to get a gauge for the size of our master. This helps us determine not only the overall size of our mold, but also what we'll need our silicone rubber to withstand. A large master means more pressure on the final mold when casting. That pressure can push our flexible mold walls out, causing deformations and slightly imperfect castings. Using a firmer, higher durometer silicone will help prevent some of that type of deformation. The material our master is made of is a key element to consider. Is it fragile? Will it break if I try to demold it with too much force? Is it porous? Will the liquid silicone rubber mechanically lock itself to our master with that porosity? For fragile masters, we may have to switch to a multi-part mold to ensure demolding is much more gentle, and for porous masters, we may want to adjust the surface finish with a clear coat or other method to smooth things out. The stronger, more durable, and more uniform our master is, the easier the process will be. Make note of the materials that make up your master. We'll revisit this information when we choose our silicone. With the overall size and material accounted for, we'll want to understand the basic physical areas of our master. Is there a large base? Is there a narrow section in the middle? This is where we'll scan our master to discover any challenges before we design our mold. As I mentioned before, go ahead and either place your master upside down or pull up the photos that are upside down that you've already taken. I like using photos here so that I can either sketch on top of them or make notes of the problem areas as I go. Starting at the bottom, using a horizontal line such as a pencil, slowly raise that line up your master. This actually mimics the pouring process of casting and will show us any problem areas. If there's a section that's isolated from the main body, you'll see this with a gap along that line, then we know that our casting material will have issues filling that area when we pour. Additionally, we know that removing our master will be challenging, especially for a one-part mold. Isolated areas like this are often undercuts that lock your master in your mold by hooking themselves inside. If while raising our line upward, we have an area that goes from larger to smaller, we also know that when removing our master, the silicone will have to stretch significantly in order to get the wider section out. For that, we'll need a silicone with great elasticity. Once we've identified all of the challenges of our master, we can compile them into one document, picture, or drawing that we call a master scan. That master scan now has all the information we need in order to determine what type of mold we'll need for this object. When scanning our master and determining our mold design, we'll often find a section of our master that sticks out from the main body, oftentimes continuing upward. These areas are referred to as undercuts, and to create a successful mold, we'll need to address them. The first issue to address is making sure that these areas fill properly. There are two basic ways to ensure our material fills any undercuts in our mold. One is changing the orientation and position of our master, and two is adding vents to our design. In some instances, simply tilting or rotating our master will ensure that these areas fill up with material instead of trapping air. To find out if this is possible, we'll simply rescan our upside-down master, this time with a slight angle or tilt added. We know we have a successful position when our scan doesn't result in any isolated areas. With our new master positioning, we can either adjust how it's positioned before molding, or in less severe cases, simply note how tilting or rotating our mold during casting will ensure that areas fill properly. However, if our tilting or rotating plan is too aggressive, then our material may spill out of our mold, limiting our ability to fill our mold completely. In these cases, we'll have to use our second option. Vents are additional shapes added to your master that allow for air that would normally be trapped in an undercut to freely rise out of the mold. Vents can be added to the master before casting, or in some cases, cut into the mold after it's fully cured. The material we use for a vent will depend on our specific project, but common materials include wax rods, wooden dowels, metal tubes, each affixed to the master with an adhesive that works for those materials. Adding vents to our mold design does ensure our castings will properly fill, but they require some additional accommodations. If our mold design is a one-part mold, then we'll have to partially cut our finished mold to ensure we can remove our castings. Multi-part molds naturally accommodate vents since their design is already in at least two halves. Adding vents will also mean that we have some post-processing to do on our castings to remove the vent and clean the area where it was attached. This is much preferred to a casting that's not completely filled, since adding material is significantly harder than just taking some away. Some simple sanding, polishing, and other post-processing activities will give us a perfect final product. Now that we've got all of our information gathered, we can begin to design our mold. For this process, I'll be using this crystal as our master. We'll use our master scan and determine the 4 key design points. Number 1, what shape of mold is best? Number 2, what size of mold is required? Number 3, how many parts does our mold need to be? And number 4, what properties do we need from our silicone? Silicone molds can be created in any shape. Since the silicone is pourable before it's cured, it will fill the container that we build. With that in mind, looking at this crystal, I can see that a simple square box shape will do just fine. The more closely our mold shape resembles the core geometry of our master, the more efficient use of silicone we'll have. That means less silicone and less money. For now, just choose a simple 3D shape for your mold, such as a cube or a cylinder. The size of our mold is directly tied to the size of our master. A common rule of thumb is to have your mold be 1/2 to 3/4 of an inch thicker than your master on all sides. This gives us enough material so that the mold will hold its shape when casting and will ensure we get the expected amount of castings out of it. Molds that are too thin will not hold their shape and often limit the amount of castings they can produce due to the limited amount of silicone material. Looking at the measurements of our master, I know that I need our mold to be 3 by 3.5 by 8.5. With our size and basic shape determined, we can review our master scan to see what type of mold will work best for our master. This crystal has a flat base and a limited number of problem areas from our master scan. Knowing this means that a one-part mold will work perfectly. If I were to tackle this cat instead, I could see that there are a number of undercuts and narrow points and full detail on all sides that would make a 2-part mold better for this master. With our shape, size, and number of parts required, there's just one final piece of our design remaining. We need to list out the physical properties required from our silicone. When it comes to choosing the right silicone for your project, there are a lot of factors to consider. However, if we pay attention to 5 key attributes, we'll be able to quickly and easily lock in a great silicone choice for our project. These attributes are 1, elongation, 2, measurement type, 3, demold or cure time, 4, hardness, and 5, cure type. We'll cover a couple of these in greater detail in the next few videos, but for now let's briefly define these 5 attributes and talk in more detail about 3 of them: elongation, measurement type, and cure time. Elongation refers to the amount that your material will stretch and lengthen. A higher percentage of elongation means that the silicone will stretch more than those with a lower percent of elongation. If our mold design depends on a significant amount of stretch to work, then we'll want to find a silicone with a higher percentage, 500% or more. Silicone rubbers require proper measuring and mixing in order to properly cure. To ensure a good result, manufacturers create their silicones to be measured either by weight or by volume, using either a scale or a graduated mixing container respectively. Be sure to choose a silicone that has a measurement style that you're equipped to handle. Kitchen scales and low-cost graduated containers are readily available and helpful tools to have on hand. The final attribute we'll focus on for now is the demold or cure time of our silicone. Each silicone rubber is chemically designed to cure at different rates. Slower curing silicones give us more time to work with our material, while faster curing silicones require focused and fast execution in order to be successful. Choosing the right cure time comes down to how comfortable we are working quickly, how much time we need to properly pour our material into our mold, and how long we have to complete our whole project. We'll cover our remaining two attributes in more detail a little later, but let's briefly talk about shore hardness and cure type before we move on. Although it might be easy to confuse the two, the hardness of a silicone and the amount of flexibility aren't exactly the same thing. The flexibility is more appropriately described with the elongation that we talked about and the hardness in combination. However, the two are correlated. The softer the silicone, the more elongation it usually has, while the harder the silicone, the less elongation it normally has. The hardness of silicone rubber is measured on a scale called the shore scale. However, silicones are not the only material to use this scale. Within the larger shore scale, there are 3 different smaller scales, each with their own letter designation. The double aught scale for the softest materials, the A scale for the medium hard materials, and the D scale for more hard and rigid materials. We have all these different scales to help sort out different materials and stuff that, we use in different casting situations and things along the way. The vast majority of silicones we use fall on the shore A scale. You can tell which of the 3 scales a material is measured on by noting the letter in the hardness measure. Within each scale, there are numbers ranging from 0 to 100, with 0 being the softest and 100 being the hardest. For a large portion of our mold making, we'll find ourselves on the shore A scale with numbers ranging from 10 to 50. Although special effects and other prop applications often dip down into the double aught scale. For a better sense of this scale, let's take a look at the hardness and flexibility of a few of our silicones for reference. Common and often safe silicone hardness to use is either 25A to 30A. However, pay attention to your master scan and mold design to make sure the hardness you choose will work with your plan. Making the right choice comes with experience, but in order to make this easier, we've created a silicone decision tree to help guide you to the right answer based on your project. It might be tempting to maximize overall flexibility of your mold by choosing a lower hardness silicone like 10A every time. Although it might be easier to demold our castings with a softer, more elastic silicone, the softer material will have less dimensional stability and will require supports in order to keep its exact shape while casting. Harder silicones often provide greater dimensional stability, limiting the amount of warping and deforming. Their hardness also means no support cradles are required to achieve accurate and precise castings. Almost every silicone rubber we use for mold making is one of 2 types, tin cure or platinum cure. Both cure types work extremely well for mold making with excellent release properties, but have their own limitations that we need to be aware of. Let's define the differences and then look at how each one performs. The first difference is cure inhibition. Cure inhibition is the inability for a silicone rubber to fully cure due to the material the master is made of. We'll talk about cure inhibition and what causes it in more detail in another video, but for reference, tin cure silicones have little to no cure inhibition issues, while platinum cure silicones have a few that we'll have to deal with. Our second difference comes in how long the molds will last in storage, something we call library life. This is not how many castings or shots you can expect to get out of your mold, but instead how long the mold will last regardless of use. We can think about this like a book on a library shelf, not being read or leafed through. Tin cure silicones have a more limited library life, from 1 to 10 years, while platinum cure silicones have a much longer life, reaching upwards of 30 years. This factor might not be the deciding factor for many of us, but if you need your mold to serve as long-term reference, you'll want to consider the difference. Library life is not the same thing as shelf life. The shelf life of a material refers to how long the silicone rubber lasts before we mix the two sides together and make our mold. The library life is how long that finished mold lasts just sitting in storage. Our third difference is a specific attribute called shrinkage. When curing, silicone rubber and casting materials can slightly shrink, making them slightly less consistent with the original master. Tin cure silicones can have a shrinkage of 1%, while platinum cure silicones have little to no shrinkage at all. 1% might not be something that even affects our project, but in extreme, high-fidelity situations like automotive or manufacturing, that 1% may mean the difference between a successful or failed casting. The cost is our fourth difference to review. Tin cure silicones are often more cost-effective than platinum cure silicones. This is not always the case and is not necessarily a measure of quality. The difference is mostly due to the cost of production. However, when beginning our mold-making journey, lower cost options can make getting started a little easier. The fifth and final difference is FDA compliance. If our project is going to be used for food or other human contact applications, then we need to pay special attention to this. Tin cure silicones are not FDA compliant due to their chemical makeup. Platinum cure silicones are often FDA compliant and the required option for these types of applications. Please note that not all platinum cure silicones are FDA compliant or rated for use on skin. It's very important that you review the manufacturer's specifications and only use the material for what it was intended and tested for. Choosing which type of silicone we want to use is as easy as running through this list. If our project is dependent on any one of these differences, well, then we need to make our choice based on that. If these aren't a factor, then our choice becomes preference. Just remember that we still need our silicone to have the other properties, like hardness and elongation, required for our project. There is nothing more disappointing than going through the entire mold-making process, getting to the final steps of demolding our master, only to find out that we've been foiled by cure inhibition. Let's avoid the heartbreak by learning what it is, what causes it, and doing a quick test to make sure we're all set. Cure inhibition is the failure of our silicone rubber to cure when in contact with our master. Masters or other materials we'll use that contain certain chemicals are the root cause of this issue. In these cases, our mold will turn out perfectly, except for the exact area where our silicone comes in contact with the master. That section of the mold will remain in an uncured liquid form instead of a cured firm form. Cure inhibition is almost exclusively a problem when it comes to using platinum cure silicones. If we're using a tin cure silicone, then we don't have to be as concerned about this happening, since their chemistry is much more tolerant of these materials. To avoid this issue, let's review a short list of the common materials and chemicals that cause cure inhibition. Sulfur-based clays and other sulfur-containing materials, vinyl, polyurethane rubbers, latex rubber, some paint products, resin 3D printed parts, polyester resin products such as Bondo, and tin-cured silicone rubbers. Although this list covers the majority of situations, there are always more. This is often due to the manufacturers using chemicals such as vinyl or sulfur in products that we don't necessarily think of. To make sure that we avoid cure inhibition in our project, especially when we're not quite sure what our master is made of, we'll simply test cure our silicone on a small area. Simply mix up a small, appropriately measured batch of silicone rubber and apply it to the master. It's best to apply the silicone in just one small section with a little bit of thickness to it. After the cure time is complete, we'll simply remove our test pour to see if there's any cure inhibition. If there is, we'll need to either seal our master with a non-inhibiting material like epoxy resin, or just use a tin cure silicone that will not have this issue. The properties and attributes of an individual silicone rubber are commonly referred to and listed as technical specifications. We've covered many of these already, but there are 4 more that we'll briefly talk about to round out our silicone knowledge. When measuring and mixing and pouring silicone, the mix viscosity will be an important attribute to pay attention to. The mix viscosity refers to how thick or thin, honey-like or water-like our material is. Materials with a lower mix viscosity are thinner and more water-like, while materials with a higher number are thicker. Mix viscosity doesn't necessarily impact our project, but instead impacts the experience we have using our silicone. Although more viscous silicones may require a longer open time to properly release any air they contain. The tear strength of silicone may be one of the more impactful physical properties when we begin using our mold. Silicones with a higher tear strength are more durable when being pulled and stretched during the demolding process. Using a lower tear strength silicone may lead to rips and tears in our mold only after a few castings. It's important to keep our mold design in mind when considering our required tear strength. Silicone rubbers are temperature-tolerant materials. Very low and very high temperatures don't affect it all that much. It's very common for silicones to withstand temperatures below 0 and temperatures at or above 400 degrees Fahrenheit. However, there are limitations. Most metals become molten at temperatures well exceeding the tolerance of our silicone. For extremely high temperature castings, it's best to use another material like sand or ceramic. Lastly, it may seem trivial, but knowing what color your silicone is matters. Silicone rubbers come in a variety of different colors, including clear and semi-translucent. Knowing what color our material is will help us make sure our experience of using that mold meets our expectations. Now that we know what the ideal silicone is for our project, let's get practical, okay? The best silicone for your project is the one you can get your hands on. Whether that's the material you already have on the shelf or the one you can quickly grab from your local hobby store, starting your project will almost always be more beneficial than waiting for the perfect silicone to come along. This can save you a ton of time and money while you gain critical experience in mold making. Oftentimes, an adjustment to our mold design will allow us to use a silicone that might be slightly harder or softer or less flexible or more flexible than we planned. If I have a 50A Platinum Cure silicone on hand, I may be able to use a 2-part mold design to achieve the same result that a 10A silicone could in a 1-part mold. If we follow the principles of good mold design, then it doesn't matter what style of mold we choose. If you give 3 mold makers the same object to make a mold of, it's not uncommon for each one of them to use a different design and a different silicone entirely. This little tree sculpture here could support a 1-part mold with a softer 20A silicone or a 2-part mold with a harder 40A silicone. The best option is the one that you can do either more cost effectively or faster depending on your situation. This idea not only applies to silicone, but also to building mold boxes, cradles, and any other materials we need for our project. Remember, the best material for our project is the one we can actually get our hands on and use. When our mold design calls for 2 or more parts, we'll find ourselves needing to use something called registration marks. We'll cover this topic in more detail during a 2-part mold making course, but for now, it's important we have a cursory understanding of what they are and why we use them. Registration marks are unique shapes added to the layout of a multi-part mold that serve to align the different parts of our mold together and lock them in place. This is often achieved by adding uniquely patterned bumps or shapes inside of our mold box before pouring, or by carving directly into the clay around a clayed up master. Now that we know what silicone we're going to use for our project, we now need to figure out how much silicone we need. Properly estimating the amount of silicone required is simple, and it ensures that we have enough silicone to complete our project without wasting a significant amount of material. Since we're working with three-dimensional objects and containers, we're going to use volume calculations. I've got full faith in your ability to do this math. I'll walk you through it step by step too, so you'll be fine. Let's start with the basic equation for determining how much silicone we need. The equation is our mold box volume minus our master volume equals our silicone volume. Let's start with the easy one and calculate our mold box volume. It's very likely that the mold box we've created is a simple shape like a box, also called a cuboid by the way, or a cylinder. If you're getting a scary flashback of high school math class, don't worry. Doing a Google search for cylinder volume or cuboid volume will bring up a handy volume calculator that you can just plug numbers into and easily use. For a more complex mold box shape, we'll do our best to break the large shape into more basic ones where the volume is much easier to calculate. We can follow the same approach when calculating the volume of our master. Breaking it down into a few simpler shapes will get us an acceptable result. You can end up spending a lot of time on this step, but I encourage you to start out just simple. Don't make this complicated. Do some quick estimates and then keep moving. You'll get better at estimating and calculating volume the more you do it. Now that we have our mold box volume and our estimated master volume, we can subtract the two to find our total silicone volume in cubic inches. When we have our final silicone volume required, there's one more step that we may need to take. If our silicone of choice is measured by weight, then we need to turn this needed silicone volume into a measurement of weight. To do that, we'll simply multiply that number by 21, since there are 21 grams of silicone in 1 cubic inch. Once we have our amount in grams, we can turn that into whatever weight measurement we prefer. But what if our silicone is measured in ounces like our amazing mold maker? No need to worry. We'll just multiply our silicone volume by 0.554 to get our total ounces required. With our exact amount of silicone determined, we'll want to make sure to add a little extra since not all of the silicone we measure and mix will actually make it into our mold. Some silicone will always stay on the walls and base of our container. The amount to add depends on the size of the mixing container we use, but 10% of maybe your total volume that you've measured out is a good rule of thumb. If we end up mixing too little silicone, we can always mix up a little bit more to finish off our mold. If we mix up too much, well, pouring that silicone out onto a surface with ample space will result in a silicone mat that can be used for messy project work. Either way, we can make sure no silicone goes to waste. The more you work with silicone rubber, the better you'll become at estimating the amount you need for the mold design you've made. As we near the end of planning, it's important to reiterate a key mindset that's useful to have when starting out on our mold making journey. Look, it can be easy to get caught up in searching for the perfect tools, workspace, materials, and pretty much every other aspect of this process. When we do this, we make it harder to get started and get learning. Working with and utilizing the tools, materials, and resources you have on hand is a great way to learn quickly, determine what style of mold making you want to pursue. This saves you time and money in both the short and in the long run. There will still be necessary tools and equipment to get started, but we'll also look at low-cost, at-home alternatives that you can also use throughout the process. The best tool for the job is the one you'll actually use to get it done. We've also taken great steps to make some of our most popular silicone products available to you at retail locations wherever you live. When inspiration strikes or if you suddenly run out of material, a quick drive to the store can save the day and keep you moving. If you want to know where you can find our products in your area, just head to alumilite.com and select Find Locally to get started. Before we jump into building our mold, we need to talk about safety. If there was one video I'd personally ask that you rewatch, it's this one. Working safely is the most important part of any mold making and casting project. Our health and safety come first. Personal safety is most often handled through the use of PPE, personal protective equipment. This includes gloves, safety glasses, respirators, aprons, face shields, and any other equipment we wear to keep ourselves safe. Every material we use in our creative endeavors requires a different amount and type of personal protective equipment. What is used when mixing silicone may be different than what we use when mixing concrete. Finding out what PPE we need for the materials we're working with is done by locating and reviewing the safety data sheets for each material. These safety data sheets can be found on each product page of our website. It's important to remember that silicone rubbers are materials that go through chemical reactions when we work with them. Treating these materials with respect and care is vital to keeping ourselves safe. The most commonly required items of PPE that we will use while working with silicone will be gloves and safety glasses, along with covering clothes. These items limit the chemicals' contact with our skin and keep us safe. However, it's important to review the safety data sheets and follow the manufacturer's guidelines for your specific material before working with it, as some require more safety precautions. Personal safety is a personal responsibility, and it's important that we take it seriously. Before beginning to work with silicones and other chemicals, it is important to take time to be prepared. That means clearing your space of other chemicals and materials, cleaning thoroughly, and having a plan in case of spills or other issues. In addition to the recommended PPE, the safety data sheets also inform us of what to do in case of an emergency, such as ingestion or another form of contact. Knowing the proper steps to take and having the equipment necessary to handle such a situation is critical to our safety. Take your safety and the safety of those around you seriously. Read the material safety data sheets, use the proper personal protective equipment, prepare your space, and be prepared for an emergency if the situation arises. If you want to stay in the know, then sign up for our email, text, and follow us on social, where you can see the latest and greatest projects, courses, and other beautiful things that people just like you are making every day. Thank you again for joining us on this course, and we'll see you in the next one.